As scientists, when we do an experiment, it's best practice to take repeat readings. So no matter what we're measuring, whether it's length, mass, an angle, or a voltage, we would take that reading a few times. Now, one reason why we do that is to take the mean average of that data set, giving you a single value for that reading. So that means to say that on average, when I take a reading for this measurement, I get this value. And because we have a bank of data now for that measurement, we know what the spread is in our data set. Now, this tells us just how accurately we've been able to take that measurement and how confident we are in that value. Now, this is the basis of error analysis, so come with me to the whiteboard and we'll do some graphs. Now, for any variable that we measure, if we take the reading enough times, we can plot the data set to see what it looks like. Now, I'll be doing that a little bit later using a histogram in Excel, and that's not really a plot that we use very often, so I'm going to walk you through exactly how to do it, but just to give you an idea of what it will look like. On the x-axis, we are going to have the thing that we measure, x, and on the y-axis, we are going to have the frequency. So this is the amount of times that we see that reading in the data set. Now in Excel, this is going to look a bit like a bar chart, and this is because we group values of x together so that we can plot a range of x values against the frequency that they're seen. Now, despite that, the overall shape is still going to look like a bell curve, otherwise known as a Gaussian distribution or a normal distribution. And it looks a little bit like, can I do it in one go? Yeah, why not? Like that. Now, in ideal cases, this would be a symmetric curve. It's pretty much symmetrical. And it's centered around the mean average. So here, bang in the middle is x bar, our mean. Now, the spread of the data or the width of the curve tells us about the uncertainty on that value. So the wider the curve, the higher the uncertainty here. Now, we can characterize and quantify the spread of this data using something called the standard deviation, and we denote that using little sigma. And this tells us about how much our data set deviates from the mean. Now, just to take that one step further so you fully understand what I mean by standard deviation, we can use something called the empirical rule or the 3 sigma rule. And this tells us that 99.7% of our data points should lie between 3 sigmas of the mean. So if I start putting some labels on here and then splitting those up into thirds, we can say that this is 3 sigma, this is 2 sigma, that's just one standard deviation, and this is minus 2 sigma, minus 3 sigma. So we can say that in this first section, in one standard deviation, 68% of our data points lie in that range. In 2 standard deviations, we see 95% of our data points. And in those 3 standard deviations, we will see 99.7%. So this is all very nice, but how do we use this information to get an error bar for our data set? Well, we can work out an error for the mean using the standard deviation and the sample size. And the equation is error on the mean, x bar, is equal to the standard deviation all over root n, where n is our sample size or the number of readings that we take. Now, it's clear from this equation that if we want the error bar to be small, we need to divide by a big number. So basically we want n, our sample size, to be large. So this is why we take lots of repeat measurements, so that we can reduce the error in our mean values. Okay, so let's take this away from the whiteboard and back to real life and see if we can generate our own bell curve. Okay, so the example that I'm using today is for reaction time, and I've got a reaction timer connected to a millisecond timer. Now, this can measure my human reaction time down to millisecond precision. Now, it's important to note here that reaction time is an example of a random error. So every time I take a measurement for this, there's going to be some variation in the answer. So it's not a systematic, consistent error. It's dependent on me, and there'll be a inconsistent, unpredictable fluctuation every time I take a measurement. So I've already done a full video on how to set this up and how it works, but just as a very brief reminder, this setup is going to time the amount of time between this light turning red and me pressing the stop button. So I'm going to take the first measurement now. I'm going to press the green button to tell it that I'm ready. And then as soon as the light changes, hit red, And that gives me a reaction time of 0.180 seconds. I'm now going to do the exact same thing 35 times and build up a data set and see what it looks like when we plot it. Okay, so I've just taken 35 repeat readings for the experiment, and collecting that data set has taken me less than 10 minutes. Now, I will say here that I've been through the data set and I've taken out the outliers. So this is the instances where I've been thinking about what emails I need to send later, and it's really thrown off my reaction time to like 3 seconds or something. So I've taken those values out, so now I've got a clean data set. Now, I've justified doing this because I'm not looking for the effect of distraction. I'm just looking for the random error in me when I'm fully concentrated, trying to take that repeat measurement. So I've got a nice clean data set, so let's go to the sheets and we'll see what it looks like.
So here's the data set for the reaction timer experiment. In column A, you will see that we've got 35 repeat measurements for my reaction time. So I've highlighted column A, and to do the histogram plot, I'm going to press Insert, and I'm going to go to Charts, and I'm going to tell it All Charts, and click on Histogram. I'm going to press OK. And it brings me up a histogram plot, and you can see that it's already trying to do the normal distribution curve, which is fantastic for a data set that's taken me under 10 minutes to collect, and it's a sample size of 35. So even with a larger sample size, you might be able to model it even nicer, but I think that's pretty good going. Okay, so on the x-axis, you can see that Excel has already determined my bin size or my interval size. If you wanted to go in and change that, you can do. We just need to right-click on the x-axis and press Format Axis. And then you can see that it gives you options for bin width and number of bins. So for example, I can click here and tell it that I want to double the number of bins. So you can see here that it's kind of now just zoomed in on the x-axis. I'm going to put that back to automatic and assume that Excel knows what it's doing. And let's label up the axes before we forget what we've plotted. So for that, I come to Add Chart Element, and under Axis Titles, I want a primary horizontal and a primary vertical. So on the x-axis, on the y-axis, we have plotted frequency. And on the x-axis, we are plotting reaction time in seconds. I'm just going to get rid of the title, and there we go. Okay, so let's run some statistics on our data set. So we are going to want to find out the mean value. We also want the standard deviation. We know our sample size n, and we want to work out our error bar. Okay, so for the mean value, we want to do the formula equals average, open bracket, and then just select all the values in column A. For the standard deviation, we want to do equals STDEV. It's a formula that Excel already knows, which is very handy, and then open bracket, and again, select all your values in column A. For n, we know that this is our sample size, and the amount of repeat readings we took was 35. And then the error bar, if we remember what we wrote on the whiteboard before, the error is equal to the standard deviation all divided by root n. So the formula for that will be equals, and then select the cell that your standard deviation's in, and then divide it by, I'm just going to put the square root in brackets so it doesn't get confused, SQRT, open bracket n, and then close bracket, enter. So this gives me a mean reaction time of 0.171 seconds plus or minus 0.002, all to 3 significant figures. So you can see that I've got a really nice low error, which should be expected from a reasonable sample size of 35.
Now you've seen that with this equipment, we've been able to model the normal distribution of repeat measurements and do some really nice statistics, all with a data set that was collected in under 10 minutes. Now, if you have more time in your lab session, you could look at increasing the sample size, so increase the number of repeats that you do, and look at how that affects the error and also how that affects the standard deviation and the overall look of the normal distribution curve. Now, I think this experiment would make a really nice introduction to error analysis. Now, no one wants to do an experiment on statistics, but if you hide it inside a fun activity such as this one, the enjoyment enjoyment factor is going to be there. Out of all of the equipment that I've used with students, I found that they typically respond best to experiments where they either have to test themselves or it's a bit of a competition, and this equipment has that in bucket loads. I also think it's really important that when students are in the physics lab, they have positive and fun experiences, and again, this ticks all the boxes. Now, if you want more ideas on how to increase engagement in the physics lab and make it a more fun place to be, please subscribe to our channel because we've got loads more to come. I'll see you next week, and thank you very much for watching.